मैं डॉक्टर अंजू अग्रवाल एसोसिएट प्रोफेसर केमिस्ट्री। आज हम एमएससी केमिस्ट्री सेमेस्टर 4 में न्यूक्लियर केमिस्ट्री के अंतर्गत रेडियो एक्टिव डिके प्रोसेस में अल्फा डिके के बारे में पढ़ेंगे। द अल्फा डिके न्यूक्लियाइड्स। In alpha decay, the parent nucleus X emits an alpha particle which is equal to helium atom, leaving behind a daughter nucleus of 4 mass units less and charge 2 units less Y. That is shifting 2 places to the left in the periodic table of elements. Thus, radium, after the emission of alpha particle, converted into the radon, which have the atomic mass number 4 units less than the radium and atomic number 2 units less than the radium. Similarly, plutonium converted into the uranium after the emission of alpha particle, and there is the difference is similar as in the former example. Bismuth being the heaviest stable nuclide in nature, all nuclides of A greater than or equal to 210 atomic mass number and Z is greater than 83 atomic number tend to decay by alpha emission, and the very heavy nuclide Z is greater than or equal to 92 do so in competition with the process of fission. Of the stable elements in the middle of the periodic table, there are some nuclides as neodymium, samarium, gadolinium, hafnium and platinum, which are feebly alpha active with very long half-lives ranging from 10 to the power 11 to 10 to the power 15 years. The range and ionizing power of alpha particles. The alpha particles in radioactive disintegrations have a range of a few centimeter in air, and about 0.004 centimeter in aluminium. The term range in air refers to the distance in air from the source. Up to which practically all alpha particles emitted transverse and beyond which their number abruptly falls. The mean range R in air is related to the energy E of the particle by the relation R equal to 0.318 E 3 by 2. As an alpha particle passes through air or any matter, it loses energy by exciting and ionizing the atoms of matter it collides with. On the average, each alpha particle produces around 2500 ion pairs per mm path in the first 3 centimeter or so of air, and the ionizing power rapidly increases to around 7000 ion pairs per mm towards the last few mm of the transit. The stopping power of medium is defined as S equal to minus dE upon dx. It is given by the expression S equal to kz log 2 mev square upon I equal to R air upon R medium, where K is a constant, Z is the atomic number of atom of the medium, Me the electron mass, V is the velocity of the particle, and I the mean excitation ionization energy of the atom of the medium. The ratio of mean ranges in air to that in medium gives the approximate stopping power of the medium. अब है penetration of potential barriers. In outline, the theory takes the following form. The Schrodinger wave equation for an alpha particle of energy E inside the nuclear potential well is set up and solved. The wave function representing the alpha particle does not go abruptly to zero at the wall of the potential barrier as are in figure 3.3 and the finite, although small, values outside the radial distance r1. By applying the boundary condition, the wave function at its first derivative must be continuous at r1 and r2. r1 और r2 जो है डिस्टेंस जो है उसके बीच में फर्स्ट वेव फंक्शन और उसका जो फर्स्ट डेरिवेटिव है must be continuous at r1 and r2. We can solve the wave equation for the region between r1 and r2. ये r1 और r2 डिस्टेंस के बीच में हम सॉल्व कर सकते हैं इक्वेशन को. That is inside the barrier, ये inside the barrier and between this distance where the potential energy is greater than the total kinetic energy. This is represent the potential energy. यहाँ पर इसके अंदर जो potential energy है is greater than total energy, and this energy is the total energy is the sum of kinetic energy of alpha particle and recoil nucleus. The probability for P for the alpha particle of mass m alpha to penetrate that region, the so-called barrier penetrability factor, यानी इस जो बैरियर को पार करने के लिए हमें इस बैरियर को क्रॉस करने के लिए हमें जो एनर्जी चाहिएगी उसे हम पेनिट्रेटिंग बैरियर एनर्जी फैक्टर से बैरियर पेनिट्रेबिलिटी फैक्टर से हम बताते हैं. This is given by the square of the wave function and turns out to be P equal to exponential ब्रैकेट में -4 pi upon h root 2 mu integration between r1 to r2 root mu r minus t dr, where mu equal to m alpha mr upon m alpha plus mr is the reduced mass of alpha particle and recoil nucleus. For it is clear from equation 3.1 that the probability for barrier penetration decreases with increasing the value of the integral in the exponent. That is the increasing with the increasing barrier height and width. Higher the barrier, the larger the difference between. In this case, we can see that for pi h or reduced mass, all the factors are constants, but only the variable is mu r t. So, increasing barrier height and width, the higher the barrier, the larger the difference between mu r minus t, and the wider the barrier and the greater the range of integration. The decay constant lambda may be considered as the product of P and the frequency f with which an alpha particle strikes the potential barrier. The order of magnitude of f may be estimated as follows. The de Broglie wavelength h upon mu v of the alpha particle of velocity v and momentum mu v inside the nucleus is taken comparable to R1. Thus, h upon mu v approximately equal to R1 or v equal to h is approximately equal to mu upon R1. If the alpha particle is considered as bouncing back and forth between the potential walls, F equal to V upon 2R1 और F equal to H upon, यहाँ पर हमने R की वैल्यू H upon म्यू V रख दी है और V इक्वल टू ये इसकी वैल्यू रखी और F इक्वल टू V अपॉन 2R1 है, तो V की वैल्यू हमने यहाँ पर रखी, तो हम इसको लिख सकते हैं F इज अप्रोक्सीमेटली इक्वल टू H upon 2 mu R1 square. Therefore, the decay constant is, this is the multiple of probability and frequency factor. तो यहाँ पर F into H upon 2 mu R1 square और probability factor इसको हमने यहाँ लिख दिया, तो हमें इक्वेशन मिली 3-2. By a more elaborate treatment, more accurate expression for F and lambda are obtained. For certain simple forms of potential energy, the integral in the exponential of 3.1 and 3.2 can be solved in closed form, and explicit expression for lambda in terms of R1, Z and E can thus be obtained. For more realistic shapes of nuclear potentials has to be solved by numerical integration. For a square whale nuclear potential of radius R1 and a Coulomb potential, so mu R equal to ZE square upon R for R is greater than R1. The heavy dashed line in figure 3.3, the integral in 3.1 and 3.2 become integration between R1 to R2 ZE square minus TR half dr upon R half, which by the substitution x equal to R half and a square equal to ZE square upon t turns into the readily integrable form 2 root t, मतलब इसको जब हम सॉल्व करेंगे और x के बराबर r हाफ रखेंगे और a स्क्वायर बराबर z यहाँ पर ये वैल्यू a स्क्वायर के बराबर हो जाएगी, तो इसको हमने यहाँ पर इस फॉर्म में हम लिख सकते हैं और इसका जब इंटीग्रेशन करेंगे तो ये इस रेंज में रूट R1 और R2 रेंज में हमें ये इक्वेशन मिलती है. तो इंटीग्रेशन ऑफ रूट टी एक्स ए स्क्वायर माइनस एक्स स्क्वायर हाफ प्लस ए स्क्वायर साइन -1 एक्स अपॉन ए रूट R1 रेंज से रूट R2. अब R1 और R2 के रेंज में जब इस वैल्यूज ऑफ रेडियाई R1 एंड R2 आर ऑब्टेन्ड फ्रॉम द एक्सप्रेशन फॉर द टोटल काइनेटिक एनर्जी T एंड बैरियर हाइट B, है ना, बैरियर हाइट B ये T टोटल काइनेटिक एनर्जी और बैरियर हाइट जो है इसको हम एक्स्ट्रा प्लॉट करेंगे इसको और इसको भी, तो ये हमें बैरियर हाइट मिलेगी. तो इसके अनुसार after substitution of integration limits and some algebraic manipulations, we obtain this equation 3.5 where Z is the atomic number of daughter nucleus.
Finally, remembering that T equal to 1 upon 2 mu B square, substitution of 3 5 in 3 2 अगर हम यहाँ रखें तो ये इक्वेशन हमें मिलती है. As an illustration of remarkable success of Gamo-Gurney-Condon approach, we saw in table a few values calculated with 3 6 and the corresponding and experimental values. The calculations were done with R1, this and with no other adjustable parameters. The agreement between calculated and measured value is seen to be within a factor of 4 in all cases except polonium, a nucleus with 126 neutron, and decay to a nucleus with 82 protons, both tightly bound closed shell nuclei that may be abnormally small radii. Even though the lambda values extend over a range of about 10 to the power 27, the in this table, these are the total kinetic energy is this radii की comparable है और calculated value जो है वो ये है, experimental value ये है. Radii were calculated from the formula R1 equal to this, and the lambda values listed are partial decay constant for the ground state alpha transitions only. The absolute values calculated depend sensitively on the nuclear radii assumed, each increased by 0.03 fm Fermi in the nuclear radius. Parameters are 0, giving rise to an approximately doubling of all lambda values. The fact that 36 gives good agreement with the experimental data when R0 is taken as 1.30 Fermi should not be considered sufficient, since 1 we used a square well potential rather than a more realistic potential shape with the tapering sides. Tapering sides है ना, the effective alpha particle radius rho alpha equal to 1.20 Fermis was chosen somewhat arbitrarily. These values जो है arbitrarily हमने चूज की, and the pre-exponential factor was derived on rather naive assumption that alpha particles pre-exist and oscillate in nuclei, one body model. The important point is that none of these assumptions, मतलब इनमें से जो फर्स्ट सेकेंड और थर्ड ये assumptions हैं, strongly affect the spectacular dependence of lambda on T, which stems entirely from the exponential in the 3-6, but they have a significant effect on the relation between lambda and R1, the effective nuclear radius. Even within the framework of one body model, much has been done to refine the derived and form of pre-exponential factor in expression for lambda. Nuclear radii deduced from alpha decay data can be expressed in the form R1 equal to R dash 0 A 1 by 3 with the R dash 0 values between 1.5 and 1.57 Fermi depending on the particular form of theory used. Since R1 is an effective interaction radius and includes the radius of a alpha particle, it is more appropriate to express it in the form R1 equal to R0 a की power 1 by 3 plus rho alpha. As we did above, where rho alpha is the alpha particle radius and is usually taken as 1.20 Fermi. The various theories then led to R0 values in the range of 1.25 to 1.35 FM. We have already mentioned that the apparent anomalies in the half-life versus energy relationship at shell crossing at shell crossing have been interpreted in the terms of abnormally small radii for closed shell nuclei. However, this is probably too simplistic as explanation, and other consequences of closed shell probably play a significant part. आज के लिए बस इतना ही. धन्यवाद.